All right, let's get started. So there's going to be a homework pushed out to Blackboard right after this class. It's going to be due in a week on February 20th at the usual 1 second before midnight. It's going to be on material in Chapter 2. Now, next week is exam week. I will not be giving an exam next week for this class, but I will be giving an exam the following week, right? So 2 weeks from today, I will be giving written exam number 1 for computer networking. My style for exams is to allow one 8.5 by 11 sheet of paper, both sides, for any notes that you feel are important to you. It will be conceptual. You will not need a calculator. Certainly will not need a computer. And it'll be on fair game as all material we've covered up to um, a week from Tuesday. Okay? All right, any questions about that? Okay, so let's continue on. So where we left off, we talked about BitTorrent and we talked tit for tat. And in BitTorrent, we have every peer can be both a source as well as a sink. And so the reason why BitTorrent gives you such dramatically faster download speeds is because every peer that joins the network, while it has a requirement, it's going to be downloading those 256 kilobit chunks of files. Each one also brings capacity to the network. And so when you're downloading not just from one source, you're downloading these chunks from multiple sources. And so in this example, Alice, she optimistically unchokes Bob, and this is that exploration part we talked about last time. Alice has a number of trading partners, and she ranks them continually based on the amount of bandwidth that she's getting in terms of downloading of information, those 256 kilobit chunks of files from other peers, the top 4. She trades with them because she wants her download to be fruitful. Right? So those who are valuable trading partners are those whom she downloads from. That's exploitation. You're maximizing or optimizing on something. And so this optimistic unchoking is the exploration part, and Alice makes a random choice and randomly unchokes one of her trading partners or potential trading partners with the hopes that maybe this person might in the near future become a fruitful or valuable trading partner. So Alice optimistically unchokes Bob, and she becomes one of Bob's top 4 providers, meaning that she has files or pieces of files that Bob needs to download. So then Bob reciprocates and becomes one of Alice's top 4 partners because there's a lot of high bandwidth exchange of data between the two, and then she starts trading with him. And so the higher the upload rate you have, the better you are because you are useful, as it were, i.e., you can provide a lot of these 256 kilobit chunks of files to those with whom you are trading, and you end up getting the files faster. Okay, so any questions about peer-to-peer? Yeah. All right. All right, so let's continue on. So let's look at video streaming and so-called content distribution networks. This is one of the huge wins, if you will, on the internet. And there are a lot of internet properties that make a lot of money from video streaming, especially in this new era of people cutting the cord, where people are increasingly subscribing instead of to broadcast TV, they're subscribing to video streaming services. And so video is a major reason for increased bandwidth consumption on the internet. If you think about something like high definition television, right? 1080p is 1920 by 1080 pixels, and each pixel is 4 bytes wide for red, green, blue, alpha, RGB alpha representation. And so if you're streaming at 30 frames per second, that means 30 times a second you're sending one of those 1920 by 1080 sets of pixels, each one of which is 4 bytes long. That's a lot of data. And so, there are about a billion, maybe more than a billion now, YouTube users, and there are about 75 million, at least of the, writing this slide back in 2017. I'm sure that's more now, but there are quite a few Netflix users, and they're all trafficking back and forth in that video data. And that's just Netflix and YouTube, but there are lots and lots of other media sites like CanCan. Hulu, and you name it, there are many more, and there are more coming online, as the years go by. And so video takes up a lot of data. It's very bandwidth rich. And so the challenge is with these so-called internet scale types of systems, how do you scale to billions of users? Or you as a singular service, how do you scale to many millions of users? Because that's a lot of bandwidth need for sending this data back and forth. And moreover, it has to be kind of relatively timely, right? Because if you get your first video frame maybe quickly, and then you say your second video frame comes in a few seconds later, your video viewing experience is not very good, right? It's very choppy. And so the other challenge is heterogeneity. Different users, right, will be streaming data on different types of form factor platforms. Some might be watching things on cell phones. Some might be watching things on tablets. Some may be on laptops, right? Maybe in the future, I can't see why now, but who knows? Maybe on a watch platform, someone might want to stream video for whatever reason, as well as desktop. Some are wired connections, some are wireless connections. So each one of these platforms on which you're viewing this rich data or video, they have different capabilities. Different bandwidth because of the connection. Some have a lot of bandwidth. Maybe you're on a desktop and you have a fiber optic connection to the curb, such as Verizon Fios type product, or maybe you're wireless in a very small form factor wireless device, and you're running on maybe 3G mobile network, right? You don't have a lot of bandwidth available. And so, how do you serve all of these different devices while still trying to guarantee some semblance of a good or relatively good or decent video viewing experience? And so the solution for this is distributed application level infrastructure. And again, you'll find for many of these internet application solutions, it's always at the application layer because it's much easier to push complexity to the edges of the network than to try to make a modification to the interior, namely the switching fabric. And if you think about it, if you can keep the switching fabric simple, you can make it very, very fast because at the end of the day, what you're after is to get reasonably fast end-to-end flows, right? And so that switching fabric, it's very rare that people make a major change to how the switching fabric works because they want to make sure that it's kept relatively simple. Okay. So multimedia. Let's take a look at this data. And so multimedia consists of a set of images. That's what a video is. And it's a sequence of images. And I mentioned 30 frames a second, but you might have some high definition video at 60 frames a second, not only just the resolution, but the sampling rate can be very, very fast. Now, certainly at 60 frames a second, that's a lot of data going back and forth. And so one of the things they try to do is encode this video so that they can efficiently depict this information from one image frame to the next in a very efficient manner. And so when you think of a sequence, it's something like 24 frames a second or images per second. A pixel is nothing more than a two-dimensional array of these so-called picture elements, each one of which has a certain color encoded as a mixture of red, green, and blue, right? And so if you take a look at an image, this particular frame on the top, it's somebody running at dawn or dusk. And from one image to the next, if you're doing it 24 frames a second, there's not going to be very much difference between one frame and the very next frame, right? The scene doesn't change very much in one 24th of a second, right? And so that being the case, when you're trying to transmit this information, you can kind of compress this stuff so that you can be descriptive and describe the full set of pixels coming across in the image without necessarily taking up as much bandwidth. And so there are two major ways people code images. One is using spatial coding, and the other is using temporal coding. Now with spatial coding, because the time between one image and the next is not very much, there are going to be many pixels from one frame to the next that are going to be the same. right? So within a single frame, in this example, the scenery that's above the sky, right? Those pixels are for the most part very close to one another over a short space of distance, a short span. And so with so-called spatial coding, instead of sending every single pixel, each one being the same value, it compresses that into two things, namely a color value and a number representing how many occurrences of a pixel at that color, right? So that means now in just 2 bytes, well, more correctly, in just 5 bytes, because it's RGB alpha, instead of having those 4 bytes repeated, say 10 times, now you have 4 bytes once plus a number, one more byte, to represent the same amount of information. And so on the receiver side, certainly it says, okay, well, you have a color description and a number. I'm just going to draw an image that has that color repeated that many number of times. And so as somebody is running, certainly some images that coding might be less effective because you have a lot of different pixels. But for the most part, as you get closer and closer to adjacent pixels in the image, they're all roughly the same color, and you can get away with the spatial coding and realize a dramatic savings in the amount of information you're sending across the wire. Okay. Any questions about this? Does that make sense? And so that's spatial coding. The other is so-called temporal coding. And with temporal coding, you're taking advantage of that small time difference between subsequent frames. Now, in 1/124th of a second, you're not going to have that much difference between what you're seeing in one version of the image versus one that's a brief moment later. And so in the case of somebody running or jogging, right, in 1/124th of a second, that person's not going to move very much and the scenery is not going to move very much. So instead of sending the entire image or even spatially coding, another alternative is to just send the deltas. You say this position changed to this value. Now, of course, if the majority of the image stays the same, instead of sending all in high def 1920 by 1080 pixels, you're now just sending information associated with that relatively small number of pixels that have changed from one frame to the next. So by sending the deltas, or what has changed from one time instant to the next, you're now realizing a savings in the amount of information that's sent across the wire, and therefore sending those updates takes up less bandwidth. Okay, any questions about this? So the first is called spatial coding, and the other is called temporal coding. And all of this is in service to sending this image data, i.e. the video, using up less or as little bandwidth as possible. Okay, and so there are different ways of coding. There's something called constant bit rate, and that means your video encoding rate is fixed. And when we say rate, we mean the equivalent of how many frames per second, right? How much data you're sending. And then there's something called variable bit rate. Now, with variable bit rate, the converse is true, that the encoding rate changes as the amount of spatial and temporal coding changes. And what does that mean? You can think of it, and here's an example, as the resolution. You can represent an image in terms of its full resolution, or you can represent it in a lower resolution, right? You ever see sometimes when you're watching a video, you see these pixels get really, really big, like really chunky pixels. What that means is that the coding rate is changing. In order to get you a video that does not halt or stop or hesitate, they change the encoding, the resolution, and that's in service to keeping that stream, that end-to-end flow going, so that you don't have interruptions in your video. Okay, and so when this rate changes, and you can think about it, if resolution changes, that means there's less information if the resolution is more coarse-grained, and that means it takes less space, if you will, because there's fewer bits in representing some version of that image. If the resolution is much more fine-grained, right, that means you need more bits to represent this image, and therefore it's going to be bigger if you're going to send it across the wire, takes up more bandwidth, okay? Or you need more storage to represent it. Okay. Any questions about this? All right, so there are different standards for coding, and each one is capable of a higher resolution and therefore when you're storing different video encoding standards for an image, it's going to take up more space. So there's this trade-off between space, resolution, and ultimately this affects your end-to-end performance as far as the video stream is concerned, or frame rate. Okay. So when you stream video, what's happening here, right? You initiate a request, and this request comes into an origin server. The origin server has this video stored in some coded form on its hard drive. It pulls it into memory and sends it across the internet back to your client. Now, certainly modern clients will do some buffering. They're going to store maybe 3 seconds to 5 seconds worth of video locally. And when it loads new frame information for the video across the wire from the origin server, it's using that new information to populate that storage, that buffer that's on your machine locally. And of course, the reason for that is that the idea is that maybe you can have congestion and loss on the network, but the hope is that there's an upper bound on that congestion and loss, and it'll represent a delay that's no more than 3 seconds. So if you pre-store 3 seconds worth of video locally at the client endpoint, then any new data comes and replenishes that buffer with the new video, and your experience at the client in the viewer, whether you're watching Netflix or YouTube or what have you, is that your video does not pause. And so the video you're getting isn't given to you directly, it's pulled from a buffer, and that buffer is filled or populated with the video coming in from that streaming video server, from the origin server. Any questions about this? Does that make sense? All right. So there's a technology called DASH. DASH stands for Dynamic Adaptive Streaming over HTTP. And at a high level, what DASH does, DASH is a method for sending video between the origin server and the client that has requested it. But the approach that DASH says is that it realizes that the conditions of the network can change. And this is also a nod to the fact that you can have different types of clients. You can have a mobile client that's low bandwidth. You can have maybe a desktop client that has a relatively fast bandwidth connection. And so what DASH does, it has different versions of this video file stored. And this video file is chopped up into blocks, and each block is coded, or maybe it's every second of video or every half second of video. It doesn't matter how big those blocks are. But these blocks are encoded in different resolutions. It could be encoded in a very dense, very high, fine-grained resolution, or it could be coded in a very low-grain, coarse-grained, very low resolution. And so the reason for that is that in Dash, the client is going to request the movie by requesting, or that video, by requesting these blocks of the movie. So it's going to get the first block, and then the second block, and then the third block, and then the fourth block. But while this media is streaming, certainly you can get congestion on the network, and so the end-to-end throughput is going to change. Now, if the end-to-end throughput drops too low, what's going to happen? Well, your video is going to be doggedly slow, and that's going to ruin the viewing experience. So what Dash does, it says, okay, it provides a mechanism to allow the client to switch to a different resolution video, a more compact coded version of these blocks of the video. And now your client can switch between the high resolution and the low resolution in order to adjust, if you will, to any sort of changing conditions in the end-to-end throughput of the pathway between the origin server to the client. So let's take a look at Dash. So the server divides the video file into multiple chunks, and each chunk is stored and coded at different rates. Some are going to be coarse resolution, some are going to be very high definition resolution. Now, high definition resolution is going to take up more bandwidth, whereas the low definition versions that are coded are going to take up less bandwidth. Okay, so each chunk is stored and coded at different rates, and so you have different versions of this video. You have the high definition, medium resolution, low resolution, and stuff in between. And so there's also something called a manifest file, and this manifest file provides URLs that will give the client information to point to each chunk of the video, as well as each resolution version of these chunks of the video. So the manifest file provides URLs for different chunks, and then the client, as it's fetching these blocks of video from the origin server? Well, it knows when it initiated the GET request, and then it knows when it's getting this data and when this chunk is completely downloaded. So the client can then use this information, the time and the amount of bits it's downloaded or it has received, and it can measure the effective bandwidth, the rate at which it's getting data. Now, the client does this periodically. It measures the server to client bandwidth. And then based on this bandwidth, it can consult this manifest and request one chunk at a time. So the client starts out saying, you know what? I choose the maximum resolution chunk or that version of the movie in the beginning. Now, I want to get a high def, high quality movie for the person that's watching the movie. And so it chooses the maximum coding rate that's sustainable based on the prevailing bandwidth conditions. And so it starts out with the maximum resolution, and then it measures the bandwidth. And if the bandwidth drops to a certain point, it says, the bandwidth is degrading. Let me select a lower resolution version of this movie when I request the next chunk or the next block. And so the client can choose different coding rates of different versions of the movie at different points in time, and this is dependent on these periodic measurements of bandwidth. And so it adjusts over time. Now you can actually see this, maybe you watch like a YouTube video, right? Or you're watching a Netflix, and you walk around and maybe you get to a part of the house where the signal is weak or what have you, you'll actually see the resolution of the movie changing. And that's exactly Dash in action. It's that client, your browser, what's running on your machine, changing to a different version or different coding rate version of the next block of the movie. And so then if your bandwidth increases, right, it gets better, then it'll switch back to a much more high resolution version for the next block. And so your client is constantly measuring and switching based on the available bandwidth. And the goal is to preserve this video the best that it can. Okay? All right, any questions about this? Does that make sense? Now, I was going to show you a Wireshark capture of Dash in action, but everything's encrypted, so it didn't really make sense. It's doing HTTP gets over transport layer security, so all you see are these big hashes, and it's not very interesting. But nonetheless, properties like Netflix and YouTube use Dash and Dash variants for their video streaming. Okay? All right. Questions? Any questions? Okay. So it's a deliberate design choice. All the quote unquote intelligence, all the decision making, and all of the heavy lifting and all the work for Dash is placed at the client, at the endpoint, right? The server just responds back with a chunk, and it can select a number of different versions of a chunk for these video file versions. So the server doesn't really know anything. It's the client. And it kind of makes sense, right? It's a smart design decision from an application and software engineering standpoint because you're going to charge the cost of the computation for all of this decision making to the person who wants to watch the video, right? Rather than putting that on the server, you keep the server relatively simple. It just responds to get this chunk of this file right now, right? It doesn't know and it doesn't care that there are different resolution versions. It just responds to it. It's the manifest that has all this information. So the client is in possession of the manifest, and all of the intelligence, the measurement of bandwidth and the choosing of different resolutions, that's all done at the client, right? So the client determines when to request a chunk. And again, that chunk that it requests is used to fill a buffer, replenish a buffer, and it's the movie that you see is actually being played from information that's pulled out of the buffer. And again, that buffer represents a certain amount of time worth of video data in effort to prevent you from having skips should the network get congested or start dropping packets of information. And so the client determines a number of things, when to request a chunk, so it knows I need the first chunk, the second chunk, or the third chunk, in addition to the resolution. Get me the medium resolution of the first chunk, and then get me the high high resolution version of the second chunk. Okay, get me the medium resolution again for the third chunk, right? And so the client knows when to request things, and it does it at a rate so that its buffer does not overflow, but it's also so that its buffer does not empty out, does not get starved. Okay. Um, it also, the client, requests the encoding rate. It knows what the end-to-end bandwidth is, the throughput between the origin server and itself, and so it knows when to request low resolution versus medium resolution versus high resolution. Okay. It also knows where to request the chunk, and this is the other piece of information in the manifest. It's going to have a number of different copies of this movie, both in high, medium, and low resolution in different places scattered around the internet. Now, the reason for that is because of redundancy, but also you want to choose a server from which to download these chunks of the movie from a server that is close by to you. Because if it's close by to you, it generally tends to be faster in terms of the bandwidth over which to push the stream of information. Moreover, because you have multiple locations encoded in this manifest file, you can also switch locations should a particular server not be fruitful anymore because maybe there's a lot of congestion. So let's say you're here in Dover, and let's say the closest server is in Philadelphia. And all of a sudden, for some reason, a lot of people in Philadelphia are watching this movie. All of a sudden, you're going to need to make another choice from where you're downloading. Now, if a link to the server in Philadelphia is in your manifest, as well as a link to a server containing the video in Baltimore, you can now switch as a client to the Baltimore server and no longer use the Philadelphia server, should you find that this Philadelphia server is no longer able to give you the end-to-end throughput that you require. Okay? So that's how you get this redundancy and the scattering around of this content, this rich content, in a number of different servers, and they're not just singular servers, they're data centers. It's called a content distribution network. You're distributing the content across a network of different servers in different data centers in different locations. Okay, any questions about this? Does that make sense? Okay, so the challenge then, of course, is how do you do this streaming? Now, the streaming, you could say naively, let me put all of the video on one large server. Okay, that might work to a point, but that introduces a single point of failure. Not only could someone attack it, but that thing's going to fall over because servers, even in a data center, can only support a certain number of concurrent users. Now, with a movie, it's not like doing text messaging. In text messaging, you send data and then you're idle. Then you send data and then you're idle. With video, that data is coming constantly, right? Over a period of time, like an hour, right? So that's a lot of data. And so certainly if you have a single server on which you put all your movie content, it's going to be a single point of failure. Also, it's going to introduce a lot of network congestion because you're not just sending individual bursts of data, you're sending data continuously at a relatively high rate. And so you also have this other issue about these long paths. Where do you place this single server? If you place it, say, in the middle of the country, that means, in the Midwest somewhere, maybe people in California and Seattle, it'll be slower because there are more hops to go over to get there to that content. And people on the Atlantic coast, it's going to be slower. Let's say you decided I'm going to put it on the East Coast, then maybe people on the West Coast is going to be slow. And so another problem that you have with a single server solution for content distribution is that you have congestion and a large number of hops, and therefore slower end-to-end throughput for people who are more distant. In fact, on Wall Street, when they implement these trading systems, they like to put it physically as close to Wall Street as possible. So they'll put it across the river, Hudson River, from northern New Jersey, so that they have the minimum latency or delay as possible for these real-time trading applications, because milliseconds matter when you're trying to take advantage of information on the markets. Okay, so you have multiple copies of a video going out over an outgoing link, right? So that's another issue. If you have a blockbuster movie with a single server, many people are going to watch it because it's a blockbuster movie. And so that trunk line over which that data goes from the data center, you're going to have a lot of copies of the same video, which kind of doesn't make sense, right? You want to take advantage of something that kind of looks like caching. You want to put the data closer to the people who are going to use that data because they're going to use it frequently and it's not going to be the only person that needs that same copy. So this doesn't scale. And the other option is to have multiple copies of that video in different geographically distributed locations, right? And so, maybe one copy somewhere in the mid-Atlantic, another copy serving large metros. So someone like New York City might have its own copy if you're a very large city. But if you don't have a lot of very large cities, maybe one data center serves an entire region. And so this geographically distributed set of copies of data managed by servers is called a content distribution network. Now, of course, you as a user, you don't know which server is sending you your data. Now, certainly now you do with Wireshark, you can fire it up and look at some of the URLs, look at some of the IP addresses, and figure out where your requests are being served from. But at a user level, you type in www.netflix.com, you log in, and you click on a video. All of a sudden, you get the video, and you don't really know whether it's served from the East Coast, the West Coast, New York City Metro, or wherever. So the so-called content delivery network, or CDN, is a method for how you maintain multiple copies of content, and you're now serving up that content from a set of geographically distributed origin servers, and it works seamlessly from the perspective of the user. And so there are different ways of locating these CDN servers. One is called Enter Deep. Now with Enter Deep, you're pushing these CDN server instances containing your content as close to the access networks and the users' access networks who are trying to consume this content. And so there's an internet property called Akamai. And Akamai, remember when they first went public, they're a multi-billion-dollar company. They deal primarily with content distribution networks. For some of you on the supplementary questions for the Wireshark, you probably saw URLs that said akamai.net, right? That's what Akamai does. They're in the content distribution business. And so you, as a rich content provider, you would call up Akamai and say, hey, I'm going to start sending course videos. I'd like to use your content distribution network. They say, okay, great. Roughly how much data you're talking about. You pay a subscription fee to Akamai, sign an agreement, give them your content, and they will handle all of the delivery of your content dynamically around the internet on their CDN network. So as of the publishing of this book in 2017, there are about 1,700 Akamai data centers dotted throughout different access networks. And the idea here with Enter Deep is to put that content as close to the users as possible, right, on the access networks. Okay, the other one is called Bring Home. With the Bring Home approach of CDNs, you have a smaller number, and you're using the points of presence to locate these CDN server instances. Recall we said a point of presence is part of this internet exchange where you have these global service providers, and when global service providers exchange data, they have a data center, and that's why you on a Verizon can send an email to someone else on Sprint network, right? Because somewhere there are locations where Sprint and Verizon locate their routers and they're exchanging data with one another. Now, in those data centers, in those points of presence, you can also locate servers for content delivery networks. And that's the other approach. There are fewer points of presence than there are access networks. And so some choose to use this bring home approach using the POP facilities as the locations of where you put your content delivery networks. And it kind of makes sense as well, right? In this particular case, you're putting the content at the seams, if you will, between two different networks, right? And so you're kind of serving both networks at the same time. Okay. And those are generally very high bandwidth connections. Any questions about this? Does that make sense? Okay. So let's take a look at these CDN nodes. And this is an example of Netflix. And let's say the movie Mad Men, which is no longer new anymore, but it's still out there. You can get it on Netflix. You have Netflix's data center somewhere in Los Gatos, California, on the West Coast, but that's not everywhere where they put their content. So Netflix will put different copies of their content, push them into many access networks. Now, consequently, Netflix, they use Amazon Web Services for their servers, right? They have hundreds of thousands of server instances, and they pay the subscription to Amazon AWS to use servers. Now, you might ask, why do they do that? Well, you pay a cost and you don't have to worry about maintaining the hardware. You don't have to worry about backups. You let someone else manage the infrastructure, and you focus just on movies, right? And so that was a decision by Netflix because they didn't want to get in the hardware business. They didn't want to get in the software business. They want to focus on the analytics and the movies, right? Zillow runs on Amazon AWS. Dropbox runs on Amazon AWS. And so there are many companies that choose to rent the server capacity rather than to buy the servers and manage those servers themselves. Because at the end of the day, the hardware costs, the software costs, and the personnel costs to manage them, that's also money. And that's an organization you have to build. Why not have someone who does that well do it for you? Okay? All right. So we have this content. And now on the left-hand side of this diagram, we have somebody who wants to watch it. So you fire up your browser, you go to netflix.com, you scroll through the interface, select Mad Men, and now you go ahead and watch the movie. So when you request Mad Men from netflix.com, what you're getting is a manifest. And so your client program looks into the manifest and it selects a close instance of a content server from which to stream this data, a nearby content server node interest. So it asks for Mad Men from Netflix when you click on the video, and you download the manifest for Mad Men, and it has a bunch of URLs corresponding to different CDN server instances, as well as the chunks of different resolution versions of that movie. And then it makes a selection of a location on the CDN and then starts to stream this movie. All the while measuring the effective end-to-end bandwidth and switching if it needs to among different resolution versions, in addition to, if it has to, different CDN node instances located elsewhere on the network. Okay. Any questions about this? Does that make sense? So all of this is happening under the covers, and you could absolutely, with enough time, certainly fire up Wireshark, log into Netflix or log onto YouTube, start watching something, and then stop your Wireshark capture. And with enough doing, you could actually figure out what's happening and when. Okay, any questions? No? All right. So you can choose a different copy if you find the network path to the CDN instance that you've selected is no longer fruitful. Maybe it can't keep up with the bandwidth that you need to have a good viewing experience. So you can switch, and the example I gave was the Philadelphia version versus the Baltimore version. Okay, so that would be the Philadelphia version. All of a sudden you get a lot of congestion, and then you switch to the Baltimore version of the CDN for streaming your video. Okay. So there's another type of CDN. One is called over the top. And with this over the top, they're essentially offering an API where this API is controlled by the client, and it offers you the ability to control this host-to-host communication. Now, underneath the covers, right, you have things like congestion, you have latency, you have delay that occurs, but the APIs they offer you give you the illusion that you have a channel between hosts and certain aspects of the communication, like the bandwidth and delay and stuff like that, are abstracted at an API level. Okay, so with this over-the-top type of streaming, these are providers like your Hulu's, like your Netflix, like your Roku's, right? They don't exist as a broadcast type of provider. They're purely streaming based, and they offer these APIs that control communication aspects of host-to-host delivery of this rich content. And so some of the challenge deals with the congestion that you can have, because while you can have a connection between two hosts, between the origin server in one data center and the client on some access network, the congestion or the condition of the routers on all the hops along the way certainly affect your end-to-end throughput. And so some of the considerations is which CDN node are you going to use to retrieve your content? If you have multiple copies in different places, what criteria do you employ as to which one you're going to select? What is your behavior in the presence of congestion, right? Certainly, how are you going to switch, or on the basis of what criteria are you going to switch between one version of the video and another? And then at what point do you just decide to cut your losses and switch to a different CDN node? And then what do you employ for making that choice? And so what is the viewer behavior in the presence of congestion, and also which content to place in which node, right? So if you have a movie that's very popular, it's a blockbuster movie, it means a lot of people are going to be accessing it. Maybe you want to have that everywhere. Maybe there's a movie that's not as popular, not that many people are watching it, so you don't want to have this sucking up storage in all of your CDN server node instances. Maybe you only place it in some of them. So all of these considerations underneath the covers should be made when you're dealing with these pure streaming-based concerns, because it's not just a simple selection of I choose this server all the time. Right? And so people might optimize this as network changes. And certainly when 5G comes online, the idea of watching movies on mobile devices might become more widespread. And certainly you're going to have to adjust because you're now putting more burden, more data on different parts of the network that never used to have them. Okay? All right. Any questions about this? Does that make sense? Yeah? All right. So there's more on this in another chapter, but in this example, we take a closer look at what happens when you access a content delivery network. And so we have Bob, and Bob wants to watch a movie, and this movie exists at some internet property in the book they call netcinema.com. And so netcinema.com has a little hash code suffix on the URL, and that uniquely identifies that particular video. Similar fashion, you'll see when you look at a YouTube video, you'll have youtube.com, and it'll say as a suffix v equals, and it has some hash number, right? That hash number is the actual identifier for the video, right? And so we have here the video identifier, and that's a suffix appended onto the URL for netcinema.com. So when you enter this in your browser, right, http netcinema.com followed by that suffix, you contact the web server for netcinema.com, and then you present it with this particular suffix on the URL. It strips that off, and it now knows which movie you want it to fetch. And so this video, while it's encoded as being on netcinema.com, it physically is stored in a content delivery network node instance, and that node instance is called kingcdn.com, and netcy, and there's the suffix, and that suffix, you'll notice here, looks similar to the suffix up above on netcinema.com. Now, of course, as a CDN node, right, it's going to have its host name, but nonetheless, that video is located at the following URL on King Content Delivery Network, or kingcdn.com. So let's see what happens. And in this particular case, we're going to use the DNS infrastructure as the way to provide this seamless mapping so that you request in your browser as a client, or Bob, netcinema.com, get this video. But at the end of the day, the right redirections are occurring in the DNS infrastructure to ultimately get that video from kingcdn.com. Okay, so let's take a look. So Bob gets a URL for the video from netcinema.com, and now Bob takes this URL and he tries to resolve it, getting an IP address for this movie. So you click on a movie and you have a URL for the movie. First thing Bob does is tries to resolve it by issuing a DNS request to his local DNS. So Bob's local DNS goes through the DNS hierarchy and ultimately contacts the authoritative DNS server for netcinema.com. And so netcinema.com's DNS says, okay, well, here's an alias, all right? Here's a canonical name, and this canonical name record entry is going to map netcinema.com with that video identifier to kingcdn.com with that identifier. So then this response comes back to Bob's local DNS server, and Bob's local DNS server then contacts, ultimately through the DNS hierarchy, the authoritative DNS for kingcdn.com. So kingcdn.com resolves this and gives back the IP address for the specific server in the King Content Delivery Network where this video is located. So Bob's local DNS gets this IP address, and Bob's client gets it from Bob's local DNS server. So now Bob knows the specific server instance in the King CDN data centers for that instance where the video is located, and then downloads the manifest and is able to stream adaptively from that CDN node instance. Okay. Any questions about this? Does that make sense? And so you can use the canonical name feature resource record in the DNS infrastructure as a way to forward you to the right CDN node instance for the purpose of streaming data. Okay, or streaming video. Okay, so here's a case study from Netflix. Now, Netflix, as I said before, uses Amazon's web services, the Amazon cloud. And so we start out, Bob logs into Netflix, to the account management server instance, and he browses Netflix's videos, and he browses that browsing using Amazon's AWS cloud instance. All of that's kept on Amazon AWS, but the login account management might be kept at Amazon. So Bob then selects a video, and when he selects the video, he downloads, his client downloads, is given by that Amazon AWS video browsing server. You hit enter on a video, you download the manifest file. And so in that manifest file is encoded a number of server instances in the content delivery network. Bob's client machine then picks one of those URLs from the manifest file and connects to one of the very many instances in the CDN network. And these CDN nodes might be managed through Amazon. It might be managed by someone else, but they're not owned by Netflix. They're rented by Netflix. Okay, any questions about this? Does that make sense? Do you have a question? Question? All right. So this is Netflix, and when you have these CDNs, you do not have to own the server infrastructure. And there are very many businesses, large businesses, that use Amazon's cloud services, and they rent that capacity. Okay, so let's segue, and we're going to look and finish with this last aspect of the application layer, and it's how do you as an application developer, write applications that make use of this infrastructure. And we're going to look at two different services, the reliable data transport service that an application would use, and the unreliable. And the abstraction is called a socket. And so the socket is an API set of functions, and it's a construct that straddles between the application layer and the transport layer. And the socket is given message data by the application, and it presents the illusion to one application that it has a direct connection that it can use to communicate to another application. Now, certainly a lot of machinery and a lot of things happen in the transport layer, the network layer, the link layer, and the physical layer to get this to work. But from the standpoint of the application, you write a piece of information into the socket, and you to send information, and you read from the socket to receive information. And so the socket gives that illusion to the communicating processes at the endpoints on the end hosts at the edges of the network, gives the illusion that they're communicating directly. Now, the socket interfaces to the transport layer, and when you want to do secure communication, what secure sockets layer or transport layer security is, what those APIs are doing is they're essentially encrypting that message data before it gets sent down into the transport layer, right? And so when you sniff such a message with Wireshark, all you see is this gobbledygook, and literally that's a hashed version of that data. You could decrypt it with enough time and enough resources, but it's not very fruitful because it would just take too long. Okay, so this is a socket. And in the book, they talk about a socket as being a door, and this door is a magical door, if you will. And you open the door and go through it, and all of a sudden, you're at the other endpoint, and vice versa in the opposite direction. Okay, and so there are two major flavors of transport services that you use that underlie a socket. And even if you don't wrap yourselves in all the details of the transport layer, well, you will on this class, certainly it's important to know the difference between these two services because like we saw in the previous diagram, the application layer needs to know what requirements it has to make the best use of the underlying framework. And so if you have an application where reliability of the data is important, things like transfer of files, things like banking, then you want to make sure that the version of your socket you use is capable of reliable transport of data. If you're dealing with something like audio, where you can afford to have some corruption in your data, then you can afford, as an application developer, to use the unreliable version of the socket. Okay, so we have these two major flavors: unreliable datagram protocol, UDP, and transmission control protocol, which is the reliable, as it's called, byte stream oriented transport. And so what happens in your application? We're going to develop a particular application. It's a very simple application, but it still illustrates the point. So the application on the client side is going to read from the command line some text. So you're going to type in a string, hit enter, and it's going to send this data to the server. The server is going to receive it. So it's going to send that text to the server, and the server is going to do some simple work, and that work it's going to do is to capitalize the text. And so it's going to capitalize that text and then return it back to the client, who's going to print it out. Okay. Any questions about this? Okay, so now I lost some time. So UDP has no connection. It has no knowledge of the connection. And this connection, no connection, means that every single packet that you send between the client and the server has to be stamped with the address where it's going to go, right? There's no handshaking, no establishment of resources, because it's the establishment of resources at the endpoint in TCP that allows you to engage in this error checking and this retrying and this assembly, right? And so UDP, because it doesn't have that handshaking, its overhead is much lower, and therefore the data that you push back and forth using UDP, you can do it much, much faster, right? And so the flip side is UDP is unreliable. It's not going to do any error checking. So if you use UDP, you could get data that's lost. You could get data that's corrupted, and none of these facilities are going to be there for you. And so if you are trafficking in something like audio, UDP is your choice. But if you're trafficking in something like a banking transaction or email and stuff like that, you're better off using TCP, because if a 1-bit should flip to a 0-bit or vice versa, you're going to get corruption, right? You can't afford that corruption for certain applications. So UDP data can be lost. It can also be transmitted out of order. With TCP, if it's transmitted out of order, it's going to reassemble that using buffers that is allocated at the endpoints. Okay, so let's take a look at a high level of UDP, and we're actually going to try this, if time permits, in real time. So we have a server, and the server is running. It creates a socket, and AF-INET means IP version 4, SOC dgram means datagram. That's the unreliable service. And that's the server running associated with an address. So the client comes in, it creates a socket, and then it sends. And when it sends, it's going to stamp every single packet it sends with the IP address of the server that it wants this message to get to. And so that message arrives, and the client reads from its server, reads from its socket, and gets the information that was sent across the wire by the client. And so the server then writes its reply after doing some work. It writes it back to the same socket. It goes across the wire. The client reads its version of the socket, or its side, or its socket, and gets that information returned to it by the server. So for each process, when you write to a socket, you're sending data. When you read from a socket, you're receiving data. And it's assumed that because it's a server, the server's already running at the point when the client contacts it, but the client is the one that initiates the communication. Okay, any questions about this? No? All right. So here's in Python what a UDP client looks like. And so it's very simple. It's easy to understand. The only thing that makes applications tricky is the application layer protocol. And in fact, we're going to have a lab assignment where you're actually going to write a simple web server in Python. So we take in the socket library in Python. We load that library. We create the UDP socket. Now you notice here the parameters AF-INET, that means IP version 4, and give it the unreliable datagram protocol, or SOC dgram. Now you can find all of this online, and lots of examples. So then you go to the command line and get input from the keyboard. And then once you get that, you return back ASCII string referenced by a variable message. So then you take your socket and you do the send to. You encode the message, and that's to translate from ASCII to some binary format that you can use to send to a disk or send across the wire. Now, this tuple here, this two tuple, has two things. It has the server name, which in our case is going to be an IP address, and you also have the server port number. Now, this port number is used by the transport layer to identify to which process you should deliver this data. So you do that send, and all of a sudden that information goes out, that packet goes out the wire to the endpoint identified that IP, by that IP address and gets delivered to the process associated with the server port number. So then the next thing the client does is it reads, receive from its socket. Now you'll see that 2048, that's a buffer size. Because you're getting data from the network, you need to store it somewhere in memory. And so you do this receive from, giving it the size of the buffer you want to populate when you get this information. And so you have the message, and then you have the server address. So then the work done is to decode this message, received back from the server, and then the client closes the connection. So the other endpoint is the server, and what the server does, the server creates its socket, and it creates a datagram socket, so they have to be matched using IP version 4 AF INET. This other step for the for the server is really important. It's the bind. And this is where the server process says, if you have information for me, transport layer, this is my identifier. If I send information, this is who it's from. And so this port number is how the application uniquely identifies itself to the transport layer, so the transport layer will know the source of a message or the destination to which that message should be delivered on the inbound side. And so you bind, and then the server sits in a tight loop, and it's continually listening for incoming connection requests. So the client on the other side creates a socket, it contacts the server. Now the server, when it does receive from, it has two sockets that are in play. One's called the server socket, and you can kind of think of it as the welcome mat. It's waiting for someone to call or for someone to make a request. The connection request comes in, and when a connection request comes in, this server socket received from, it's a blocking call. It unblocks, meaning it starts running once an incoming connection happens. And so the incoming connection happens, and you get a client address, and you get that server socket, you get that message from the server socket. You do the work of turning it into uppercase, and then you encode that message and send back down the server socket. So that's the unreliable service, and it could be that the client, when it sends its message, it completely gets lost, right? And that's just part of how UDP works. You just have to deal with that as an application writer, but you do get speed. Okay, so I just talked about that. I'm not going to go through that. And so the client must contact the server. Let's look at TCP. So when you are using TCP, underneath the covers, there's the establishment of resources. And that's called handshaking, and that's handled for you in the socket. Now, the client has to contact the server. It's the one that initiates that contact, and the server waits for this incoming request. And so the client contacts the server to establish these resources to engage in this reliable transport protocol. When it first contacts, it's asking the server, do you have the buffer space, the timers, the variables, all of the things that are required to engage in reliable exchange of data. And so when that socket returns, that means that the server is able to satisfy the resources needed to do that, and then the client subsequently now exchanges information with the server. So when the client creates the socket, it establishes the connection to the server, and then when the client is contacted, a new socket is created in the server, and that's called your connection socket. So there are two types of sockets in play on the server side. There's the server socket, and then there's a connection socket, and the connection socket is created for every unique client that contacts that server. Okay, so let's take a look at what this looks like. Here we have the server running at some host, and the server starts out by creating its server socket, and then it's going to bind to a port number, and now it does an accept. An accept says it's going to block, and it's going to wait for incoming requests. And so the client then goes ahead, it creates the so-called client socket, and now once that client socket returns, this handshaking has happened, the connection setup or establishment, as it's called, between the client and the server. So as a result, the server returns back a server socket, and the client now takes its socket and starts sending requests. When the server returns or unblocks from accept, you get a unique connection socket. And so now the conversation between the server and the client is between the connection socket for the server and the client socket on the client side. If another client comes along and initiates a connection, a new connection socket instance is created. So typically in modern servers, you're going to have multi-threaded implementations where a unique thread is managing each connection socket between the server and the client that happened to initiate the request. So then the client writes to its client socket, sending data to the server. The server does some work and sends back a reply in the reverse direction by writing to the connection socket. Now you'll notice here this sort of edge here. Once you hand out a connection socket in the server, you now have a channel of communication with the client, but you can go back in a loop and continue to accept new incoming requests, each time creating a connection socket. Okay? Any questions about this? Yes. Yes. Well, I wouldn't say popular per se. If you want reliable communication, TCP is the predominant one on the internet stack. Now, there are differences between IP version 6 and IP version 4, but for reliable communications, TCP is the most predominant. Okay, any other questions? All right. So this is what the client code looks like in Python, and we're going to try this out. Let's see. You have your server name, and we're going to use a host name and IP address. You create your stream socket, and that's different when you create the socket. It's not sock dgram, it's sock stream. Now, sock stream is a parameter value you specify in Python when you want a so-called stream socket, which refers to the reliable version of transport. So the client then connects, and when the client connects, it specifies a tuple, a two-tuple, consisting of the server name and the server port. You take the raw input from the keyboard, and then you encode it in a binary format and send it across the wire by doing a client socket send. You read from that socket back the response back from the server, and then you print it out and close the socket. Now the server is a little bit different. We have a port number 12,000, and so we create the server socket here using AF INET, which is IP version 4, and we say sock stream, which is for a stream socket. So when we bind the server, we're going to bind to a port number, and that's reserving port number 12,000 in this case as the port number associated with this server. So then we do a server socket listen, right? Now the server socket is ready to take incoming requests, and we do the accept, and when the accept unblocks, we now get a connection socket. And that's what the server is going to use, the connection socket, to communicate back and forth to the client socket. Does that make sense? So then we take this connection socket, we do a receive and a decode. So we're getting the message when you're reading from the connection socket. The server is getting that request from the client, does some work, converts it to uppercase, and then sends back the result and closes the socket. Now you notice here, this while true, this will keep spinning again and again and again because you're going to have more than one client contacting this server, right? And in a threaded application, mind you, this isn't threaded, but in a real application, you would have unique threads handling the connection sockets once they're created as a result of the incoming request being satisfied. Okay, so let's try this out. And I've already written a client and a server, but I think it'd be more interesting to have one of you implement the server, tcp server.py. So this is my server, and it's exactly the code that I showed you, and it's going to assume the IP address of my machine, but perhaps we can have somebody implement the client, and this is what the client code looks like. I don't know if any volunteers. So if you bring up a window, no, yes. Okay, so while somebody's doing that, I'm going to bring up a new shell window and just run that, and new window, homebrew. Let me put the code right here. And so for the client, the IP address you're going to use is going to be the IP address of my machine, if config-a. And the IP address of my machine is going to be en0. It's going to be 10 10.33.17.9, right? And so for your version of the client, for server name, you're going to use this address and not the 127 address. So in the meantime, let me run my server, tcp server.py. All right, so server is ready. And it's not very interesting when I run the client and the server TCP client on the same machine. It's more interesting when it's different machines. But, oh, classes. Um, Let me, there you go. All right, TCP client.py. So I run the client. Oops. TCP client.py. I run the client. This is test. I hit enter, and that's my response back from the server. If you look at the server, ready to serve, it got the incoming request, and this is what it started with, and this is what it returned back to the client. So there's my server. It's a very simple server, and you could certainly point anybody's client at my server by just having server name changed to my 10.33.17.9 address. And so if someone is able to get that running, I'm running Python 2.7, just type your name or something like that, and it'll capitalize it so we'll know who it is. Yes, question. The IP address, I did in the command line if config-a, and it gives you all of the addresses associated with every interface on your machine. And so you bring up a terminal window. I think on Windows it's ipconfig or something like that, but you can Google search it and find out. But each interface has a string name, and on Apple version of Unix, it's BSD Unix underneath the covers for Mac OS. EN0 is the wireless interface. And so here you'll see INET, which is the IP address or the network address, and it's 10.33.17.9 in my case, and it'll certainly be different for each person. And so you can go in and look up the address, but if you're running the client and the server on the same machine, which I'm doing now, you can use what's called the loopback address, which is 127.0.0.1, and that's reserved for when the client and the server are on the same machine, because the operating system makes optimizations when it sees that the client and server are on the same machine. You don't need to use I/O and go to the network card. You can just use shared memory and make it much faster. And so you will certainly use whatever address is the address of the server when you specify a server name for your client implementation. Okay. Any other questions? Anyone able to do that? No? Okay. Let me see what time we have. It's 1:10. We have 5 minutes left. And so you could certainly try it out yourself. I hope you do. We will have an assignment where instead of a server that capitalizes things, you'll actually implement a simple web server where you'll actually parse out the GET request and fetch files off the disk and actually deliver web pages to show you that a web server is nothing special. It's just a server whose work is to retrieve files and send them back formatted as HTML. No questions? No? Okay. So we have 4 more minutes. Uh, if no one's able to do it, I can just end there. If someone's interested, I can certainly leave this up for another couple minutes. So this is Python. I'm running Python 2.7. Python 3.0, the print syntax would be a little bit different, but it's the same same API calls with the socket, the send, and the receive. Okay? All right. Any questions? No questions? All right. So with that, if there are no questions and no one wants to try it, then I'll end there. And I will see you all on Tuesday.